with the basic definition of the gradient behind us, let's use it to compute some information. Let's find the gradient of this function at this point. So let's just kind of walk through it. Remember that the gradient of the function is simply the component-wise partial derivatives. So the I component will be the x partial, or the partial with respect to x. The j component will be the partial with respect to y. So if I get the partial with respect to x, then we're going to have to use like a product rule here because I have an e to something and an x. So that'll be 2e to the y over x plus 2x e to the y over x times the derivative of y over x, which is negative y over x squared. We can do a little bit of algebra here to simplify that to get 2e to the y over x, 1 plus, or rather, looks like minus 2, or rather, y over x, like that. So then when we take the value at 2, 0, well, you have 2e to the 0, 1 minus 0. So you just end up having 2, which is kind of nice. And if we take the partial with respect to y, well, everything else is constant except for that e function. So we have 2x e to the y over x. And then we have to take the partial with respect to y of this. But everything is constant but that y, so it's just 1 over x. So that's 2e to the y over x. So our partial at 2, 0 is also just 2, which tells me that my gradient is 2i plus 2j. Okay? Let's compute a gradient here. So I need to get my partial with respect to x. Well, the derivative of cosine is negative sine. And then through the chain rule, we take the derivative of what's inside. So that's 2x. So 3, negative 4. Well, 3 squared is 9, negative 4 squared is 16. So 9 plus 16 is 25. So we end up with negative 6 sine of 25. The 3. All right. So partial with respect to y is also negative sine x squared plus y squared times 2y. When we plug in a negative 4 there, we get 8 sine of 25. All right, that sine function stays the same. Negatives cancel. So our gradient here is negative 6 sine 25i plus 8 sine 25j. Just always remember when you're computing a gradient, your result will be vector. In both these cases, we have a vector. And I said all that because when we compute a directional derivative, that is a number, it's a scalar value, because it's a dot product. So we need to find, remember that the directional derivative is the gradient dotted with the unit vector in that direction. So PQ is not going to be a unit vector, so we need to write it like this. Anyway, so we're going to compute the gradient, we're going to find the unit vector, we're going to take a dot product. So we need to find the partial derivative with respect to x. And we're going to find it at the point 1, 2. So that gives us 2. We need to find the partial with respect to y. It's going to give us 4. Now we're going from here to here. So that tells me that PQ is 1, 1. And the magnitude of that is square root of 2. So the unit vector looks like that. So then we can take the directional derivative of g in the direction of PQ by taking 2i plus 4j, or rather, let's write it like this. Let's write it as 2, 4 dotted with, so instead of writing it like this, I'm going to write it as square root of 2 over 2, square root of 2 over 2. So that's going to make my life a little easier to deal with. And so the value of that derivative in that direction is 3 square root of 2.